Everyone, welcome to the second day of TMLS 2020. I'm Beta, an ML researcher and data scientist at Ryerson University. I'm honored to be your host for this session and introduce one of our greatest speakers. During the talk, if you have any questions, post it in the chat section. I will make sure that at the end of the talk, we get back to all of them. And now let's start by introducing Benedikt Koller. He's as he calls himself, he's a seasoned SRE Ops with 11 plus years of experience in data-centric companies. Currently, he is CTO of maiot, a Munich-based AI startup, which originally focused on predictive maintenance and asset optimization of industrial assets and commercial vehicles. Currently, they're making their internal tech stack available to a broad audience. Without further ado, back to you, Benedikt.
Yeah, thanks for this kind introduction. Hello, everyone. Good morning or good evening, good night, depending on which time zone you're in. Let me jump right into the slides so that I can actually give you something nicer to look at than just my living room. While I'm sharing my presentation, I can introduce myself. So I'm Ben. You already heard the introduction a bit. I'm the co-founder here at maiot, and we're the team behind an open source MLOps framework. And today I'm going to talk a bit about some ancient history, especially of our company. When we started out in the predictive maintenance spheres, I will tell you a bit about our early days, and especially about the first year and the first 1,000 pipelines that we ran and what we could learn from that. But before we jump into that, let me attach to what Peter said about me. So I'm really an Opsguy. I went from being an old school sysadmin to being an SRE and a platform engineer in various companies. And my world is all about structure and coding standards and tests and pipelines and automation. So keep that in mind as it might color my talk a bit. And so jumping back, when I met my co-founders, and let me introduce them as well. So I met my co-founders. One is a mechanical engineer, and he came from the industry, and he had a strong vision that he wanted to transform the industry that he was coming from. And the other guy is an ML guy. He was fresh out of university and had his head full of applications for machine learning models and how to change the world with them. So with our three backgrounds, we set out to revolutionize the commercial vehicle industry. And we vowed that no vehicle should ever fail again to, for example, delay the Amazon packages that you're about to order because tomorrow is Black Friday, right? So this gathered interest from the industry, and we had, we had three guys. We were confident, and we had a very healthy dose of random forest that we cleverly disguised as near sentient AI by taking a page out of every marketing department's book. And so we got proof of concepts, right? And I was completely thrilled about that. I didn't have much interaction with machine learning up until the point when I met my co-founder. So my co-founder, realizing how thrilled I was, sat me down and fired up a Jupyter notebook, and we got to work. And he imported pandas and sklearn, and we read data from the CSV, and we did some analysis, some PCA here, some NumPy magic there. We jumped through the cells. It was a whirlwind of things, and in the end, we fitted a classifier and got amazing results. And this is what this looked to him. However, to me, this was a bit different. It felt like we could never reproduce this. It felt chaotic, and I was a bit baffled by how machine learning was done. So fast forwarding a bit, we got a second proof of concept, and that was amazing. However, my fears actually came true, and we couldn't reproduce what we had done prior. We could not just take the same Jupyter notebook and swap out the data and magically come to similar results. No, we have to reintroduce and re-implement many of the steps that we've done to account for the various nuances that are just tripwires in the field. So luckily, we were a very iteratively driven team, and we had the chance to look at what was going on here. So in machine learning, if you want to break it down into its atomic meaning, you have these individual processing steps, and they depend on a previous processing steps results. And in the end, they produce a unique artifact. And all of a sudden, I was happy again, because that's what I know. That's from my field of expertise. It's basically the DevOps build pipeline. So we took that chance and we started to build pipelines. And therefore, I'm here now to tell you the story of the first 1,000 pipelines that we ran and what we learned along the way. As a preamble, before I get too deep into it, I think it's always important to take a step out before you get to work in solving the problem, and to zoom out enough that you can actually fully grasp what the problem really is that you're trying to solve and what your motivation is, and to get to this solution. And for us, and I think it is true very much throughout the machine learning world, the key motivation for introducing something like pipelines is reproducibility. For us, that meant moving very fast from one POC to another, or to transition very fast from one experiment to another. But it really reflects into basically any workflow, no matter whether you're working with clients or in an internal setting. Okay, let's talk about pipelines. Before we ran the first pipeline, we had to start somewhere, and our start was standardization. We wanted to convert known good code into something we could reuse. Our PTSD from these early proof of concepts was still quite fresh, and we really wanted something that lasted, right? And we set out and we built these rather powerful abstractions for splitting, even in complex scenarios, so that we could categorize very easily and could split very easy, even in complex scenarios like a categorical split or index split. And we didn't stop at splitting. We moved even further up to our pre-processing steps, so that we had these known good abstractions for resampling, filling, label tuning, you name it. That served us very well. We got moving very fast, and the project that we were in at the time came to an end. The second project came around, and we're now at roughly pipeline 25. And we realized, okay, our team was growing. We were having data scientists. We were working with working students. So the key problem that we now faced was reusing entire pipelines. We didn't want to just have pipelines run on an isolated developer machine and be trustworthy there, but we wanted to be able to run them also maybe in a cloud, or I wanted to be able to rerun the same pipeline as my coworker did. So we took a page out of my ops background, and I have to admit my admiration and fandom for Terraform. We took a page out of their book, and we introduced immutable artifacts in the form of pipeline configs. So all of a sudden, you didn't have to just copy or import code into a Jupyter notebook or into whatever script you were building. You could write a config and share that with me, and I could just plug in the config into my clone of our pipeline repository, and I was able to reproduce the pipeline from data to the exact model code version that I was running and receive similar, if not the same, results. Cool. Now we're moving a bit faster, right? Because we can reproduce across machines. But what we did not account for was we got huge data. New client, new project, amazing news for us, right? But we got a huge chunk of data. And if you think about it, if you receive a terabyte of data, just running through that entire set of data once to split and pre-process actually can consume so much time that the majority of the allocated project runtime would be eaten up just by that processing step. So we realized we had to move faster, and we chose to implement distributed processing. Why could we make that choice? Because we had standardized early on. So we were already capitalizing off of the work the second time that we did in the first shot at pipelines. And the good thing is we didn't have to reinvent the wheel here, right? There are powerful abstractions out there of Spark, Hadoop. And we actually chose Apache Beam. If you're not familiar with it, it's a Google-backed project, and it has the nice advantage of having a native integration in Google Dataflow. We were running at Google Cloud back in the day. So this was a very instinctive choice for us, but it also has support for running workloads on Spark and Flink. So even moving out of this Google ecosystem would be possible for us. And most importantly, the syntax of pipelining is actually very, very comprehensive, and I can just encourage everyone to check it out because it's well done in my way. So to summarize, we were now able to run distributed pipelines for our split and pre-processing workloads. However, we don't want to distribute everything, right? If we're just doing something on a tiny data set, if I'm just running a small proof of concept on 50,000 lines of data, I don't want to spin up dozens of workers in the cloud. I just want to be able to run this in one VM or even locally on my laptop while I'm in the train. So we had to introduce these processing backends in a very modular way so that we could decide ad hoc per pipeline where we would execute the workloads. And we were successful to cut that short. However, after the first successful pipeline, we immediately realized that training a machine learning model on a huge set of data on a CPU is no fun. So immediately after introducing training backends, processing backends, we had to introduce training backends. Again, I mentioned we were running at Google Cloud, but it's really no different to AWS or Azure for that matter. There's Google AI platform, there's AWS SageMaker, there's the entire Azure MLOps toolkit that's growing by the day. So we built a similar integration as we did for our pre-processing for our training so that we could harvest the GPU-based power of these training backends in the cloud. And the same hurdle was given to us by our own thought structure. We had to be able to train locally as well, right? I don't want to necessarily train every data set that I'm working on in the cloud and incur cost. And cost is really the perfect transition now to a bit fast forward. So we were using on this big data set a lot of VMs. We were bursting quite heavily into Google Dataflow. And we realized that we've gotten faster, we haven't gotten that faster because we had to do each split and each pre-processing step over and over again. And not just was that costing us time, it also was costing us real heavy money. We were racking up crazy skyrocketing cloud costs. So we could have gone for a bit more crude approach here of just manually attaching a training to previously run pre-processing. However, that would have completely defeated the purpose of why we were pipelining in the first place. So we opted to go very heavy into tracking. I already hinted at our configs, and they might be seen as a crude way of tracking, but we went all in and integrated tracking into every aspect of our pipeline so that we could actually dynamically, while a processing step is invoked, look up whether that split, that processing step in that configuration had already been executed, and look up the artifacts in our unified artifact store and just reuse what we've done prior. And we actually were able to save a significant chunk of our cost. We reduced our own cost by up to 80%. So fast forwarding a bit, after this huge data project, we got a very big contract with a public transportation agency here in Munich, and many eyes were on this project. There was public funding included, and it was just in general a very prestigious project to begin with. However, our whole worldview got flipped upside down a bit with this project, as the assets that were in the field were streaming data, and they were streaming that data straight to us. Prior in projects, we had static data sets, so our select star from whatever was good enough to make sure that we had the same data available in our pipelines. And all of a sudden, that went away. Yeah, you could run a pipeline and you could rerun the same pipeline 5 seconds after, and you would have a different data set available, and you could not reproduce what you had done prior. We had to introduce data versioning. And before I talk about it, yes, we were aware of projects like DVC, which is great. However, it created an overhead that we shied away as an organization, and therefore decided to rather go and reuse the logic that we had already introduced for caching and adapt it for data versioning. So we really used this caching mechanism to create immutable snapshots of data, and therefore created this reusability through our pipelines without actually having to change any of our pipeline code. And while I'm in this project, a second thing happened, and it happened very far down the line. So the project was running very actively, and we were achieving good metrics across the board. But in a deep drill down with one of the project managers at the time, we realized that one of the assets that we were predicting on was a complete outlier, and it behaved rather badly when looking at the individual predictions that we were making. So through unfortunately lengthy process of hacking together visualizations and understanding what our pipelines were doing, we found out that we had introduced bias. And that caught us a bit off guard, because we were quite diligent actually in evaluating the results of the pipelines that we were getting. However, because we did not have a standardized evaluation methods, we just missed the outliers that we had created ourselves. And to remedy that without losing the freedom that the evaluation just needs at times, we sat down and really drilled into which tools do we think are best suited to root out bias going forward, and added it as a post-processing step to our pipelines. In our post-processing steps, a Jupyter notebook is created to stay within the paradigm of data scientists that features TensorBoard, TFMA, TFDA, and the what-if tool to make sure that we can catch bias with this minimum set of evaluations that just should be walked through with every pipeline that's evaluated. And coming to a bit to a close here, as a last topic, I want to talk about serving. So I'm coming from a DevOps side, I've mentioned that now. And in the DevOps philosophy, it's really all about ownership of projects and software. So we wanted to create the same ownership for the teams that were running our ML projects, and have it go from negotiating in which form data actually ends up at their project to how it's deployed, and to be responsible for the deployment when it actually happens. And for a successful serving to fulfill our criteria, serving had to meet certain aspects that we were keen on. So every pipeline had to be deployed. That needed to be guaranteed. So we had to introduce strong automation. And not just that we have to introduce strong automation, we also had to introduce automation on a level that is discoverable for the data scientists, not just the ops people. We had that before we were introducing, including the models that we trained into simple containers, but it wasn't discoverable for the data scientists in charge for these projects. So we had to flip the paradigm and actually start serving from our pipelines, so it was visible what was happening to our data scientists. Not every pipeline needed to be served. I think that's also clear, but we wanted it to be default served with an optional opt-out. And last but not least, we did not want our pipelines to go straight to production. That is, I think, a reckless move, but rather we wanted to deploy pipeline results in serving scenarios that mirror production as closely as possible. So let's say we were creating new environments on a Kubernetes cluster, introducing a already production-ready deployment that could be tested with impunity by our data science team, with a later possible handover to the stakeholders down the line, so they could actually make the decision when to swap a deployment to live. So that was quite a mouthful, and we're getting to the slide that can be screenshotted if you don't want to share the video with anyone. To zoom out, what we learned from building these pipelines is really understand the goal of building pipelines. And 9 times out of 10, I will guarantee you it's reproducibility of results. And what does need to happen to achieve that? To rehash, versioning needs to happen. And not just on the code that you're running or the models that you're producing, but also on the data that you're training on to be able to truly reproduce what you were doing and to iterate fast. You also have to standardize and reuse code, but also attach it to configurations so that you have reusability across environments. You need to build in tracking, not as an afterthought in a spreadsheet, but actually deep into your stack so that it happens automatically and gives you access to artifacts across all pipeline steps. We recommend to leverage backends for compute-intense tasks. Because sometimes you just need to burst, and there are plenty of great backends out there, from Dataflow to AWS EMR or just plain old Spark. Evaluation needs to be treated as a first-class citizen when you're constructing pipelines. It cannot be an afterthought. It needs to be baked into the very fabric and needs to be exposed to your data scientists in a digestible way. And last but not least, and this is kind of my favorite topic here, you need to create ownership and autonomy in the teams that are actually running the project so that they can own what they are creating and therefore drive business innovation going forward. So as a closing thought, since Pipeline 1000, we have stayed busy and we actually pivoted away from the predictive maintenance scheme. We built an entire product out of these and many more of our learnings. And if I can give you one advice, don't build it yourself. Everything in this talk and many more learnings will be available as an open source MLOps framework. So stay tuned, check it out, and give it a GitHub star. So, questions, anyone?
Thank you so much, Benedikt. I really enjoyed the talk, and now let's get to the questions that we get. I will start with the more general questions. Our first question is there any reason that you went with Apache Beam versus, for example, Airflow? Mm-hmm. I mean, the cloud data flow as a versus the cloud composer as like Airflow.
Yeah, that's a great question, actually. And in hindsight, I cannot entirely answer that. And I must admit that we did play a lot with Composer and Airflow. We also played a lot with Kubeflow because these are just really important players in the market. However, our goal was at that time not to find an orchestrator of our workloads. Our goal was to parallelly process the workloads that we were orchestrating ourselves already. So I think it's important to distinguish here between the purpose of what Spark and Dataflow are solving versus what tools like Airflow and Kubeflow can offer in comparison.
Thank you so much. And another question is that, can you share a suggestion with regards to open source frameworks on top of which you would recommend building such pipelines? Mm-hmm.
I'm super happy to. The open source space is moving quite fast. Just yesterday, the news broke that Tecton and Feast are collaborating. So the former Uber guys are now working with the Google guys on building a feature store. And Selton Core is a quite excellent project out there. So, but to zoom out, I think the bigger response to that question would be, you need to understand what you're going after. Is it that you already have a bit of a tech stack in your environment and you just want to introduce a vertical solution for serving, for example? Or are you really coming off bare minimum Jupyter notebooks and it's all chaos? Then you might go for something that covers the workflow end to end. And obviously you have to shamelessly plug us at this point, but also Kubeflow is great. It's been around forever, and they're doing really great work. So yeah, there are many out there. You have to see what your requirements are.
Yeah, I agree. Thank you. How did you update the models in the architecture? Will it be incremental? Online learning be possible using the current pipeline that you proposed?
So at the point where we left off, which was pipeline 1000, that was definitely not possible back then. We had a mix of well, online predictions, but on a REST call basis, and we had batch inference pipelines that we kind of hacked together back in the day. And really, I must admit, in the time that we've worked on projects, we never reached a point where online inference pipelines were really that necessary. So yes, it's possible and actually quite easy to transition a pipeline if you build it in a distributed way by attaching it to, let's say, a PubSub topic for inference. But usually these scenarios are not necessary and very, very hard from an ops perspective even. So I'd recommend to thoroughly think about what you're doing if you're moving towards online inference pipelines.
Yeah, thank you. And another question is that, do you also provide pipeline components for data preparation, especially for ingesting data streams with a high amount of noise, outliers, and sparsity?
Yeah, I think that's going to be the golden goose egg to go over data very efficiently when it comes in sparse. And I can very much relate to that question. I can give, I think, another hour of talking just about the weird ways we receive data from the clients that we were working on and the amount of pre-processing that we, or ETLing we actually had to do to make data readable. The pipelines that we're building offer the ability to run arbitrary steps, either in pre or post-processing. So you can bake that in. However, as a recommendation, I think it's a separation of concern that's necessary here to establish a feature store of some degree, especially when you have such a complicated scenario in your own organization.
I agree. And again, a more general question is that we have a couple of questions about do you leverage, for example, GCP AutoML for any of more basic use cases? Mm-hmm. And what is the difference that you see from the MLOps services offered by, for example, companies like Google or Amazon, with what you currently use and propose? So the offerings that Google, Amazon, and Azure, and I'm just going to bunch them up now because I don't want to get too much in the weeds there. The way the offerings actually range quite a bit. So there's AutoML that was mentioned in the question, which is great to move fast but doesn't let you go so deep. And then there is something like the AI platform, which is really just a bare bones way of running a container to train a model in a scenario where you have access to powerful GPUs, right? And depending on how your team is composed and how your use case actually looks like, you might want to swap out AutoML rather sooner than later to get you further. Don't think about what you need to do in the next 10 pipelines. Think about what you need to do in 100 pipelines or in 1,000 pipelines and try to build your system in that way. Yes, you're right. I completely agree. And it seems that we have covered all the questions.
Cool.
Thank you again, Benedikt, for the great talk. And thank you all for joining this session. I thank you all on behalf of TMLS and hope to see you again. Thank you so much.
Thanks everyone for listening in. Have a great conference, and make sure to check out more of the other talks.
Thank you.
Thank you. Bye-bye.
Bye.